Hello, this is the section 5.2 lesson. In this brief lesson, we're going to talk about the logic behind testing a claim about a single population proportion using the p-value method. So to illustrate this, we're going to look at this claim that we saw back in section 5.1, that more than half the students at a particular university are from out of state. And so the parameter of interest is p, the proportion of all students from this university that are from out of state. So the hypotheses are the null that p equals 0.5, and the alternative is that p is greater than 0.5. So to test these hypotheses, we went out and collected some data by surveying 95 students and found that 62.1% of them are from out of state. Now this sample proportion of 62.1% is what we generically call the sample statistic. Now let's make an observation. This sample proportion of 0.621 is larger than expected, assuming the null hypothesis is a true statement. We can think of these hypotheses as being two competing mathematical statements. For the sake of argument, we're going to assume that the null hypothesis is a true statement, and we're going to base all our calculations based off of that assumption, and then based off those calculations we're going to determine if that assumption is reasonable or not. Okay. So this sample proportion of 0.621 is large, assuming the null hypothesis is a true statement, but is it unusually large? Well, to answer that question, we're going to use this unusual event guideline that we first saw way back in Chapter 2, which informally says that an observed number is unusually large if the probability of it or more is small. And small here typically means like less than 0.05. So we're going to use this unusual event guideline to calculate the probability of observing a sample proportion at least this large, assuming the null hypothesis is a true statement. If that probability is small, then that means that this number is unusually large, which means that our assumption is probably false, and so we're going to reject that assumption. If this probability is not small, then that means that our observed sample proportion is not unusually large, and we will not reject the null hypothesis. Yeah, so again here, just to summarize, if this probability were small, meaning that this sample proportion is unusually large, then we would reject the assumption. Or stated in other words, we would reject the null hypothesis. On the other hand, if this sample proportion is not unusually large, then we would not reject the assumption. Or in other words, we would not reject the null hypothesis. Okay. So to this end, let's generalize our calculations here a little bit, and suppose the null hypothesis is of the form p equals p naught, where p naught is some given number. Okay. And so to collect data, we go out and we ask a bunch of people a question, and let's define the random variable x to equal the number of successes in a sample of size n. And so in this particular example, a success is getting someone who is from out of state. So we go out, we ask each person, are you from in-state or out of state? And so each person is either a success, meaning they're from out of state, or they're not a success, meaning they are from in-state. And so in other words, assuming the null hypothesis is true, then this random variable x has a binomial distribution with n trials, and the probability of a success is p naught. Okay. Well, now by theorem 441, the sample proportion p hat, which we define to be x divided by n, has an approximately normal distribution with mean p naught and variance p naught times 1 minus p naught divided by n. So let's suppose that a sample proportion lowercase p hat has actually been observed. And so to determine if that sample proportion is unusually large, we need to calculate the probability that the random variable, capital P hat, is larger than this observed value, lowercase p hat. Okay. Well, this random variable, capital P hat, has an approximately normal distribution. And so to calculate this probability, we need to calculate a z-score. And so we take the number inside the parentheses, subtract the mean, divide it by the standard deviation, and that's our z-score. And so then the probability that we want is equal to the probability that z, a random variable with the standard normal distribution, is greater than the z-score. And so this probability here is our p-value as we defined it back in section 5.1. So this leads us to an informal interpretation of the p-value. The p-value is the probability of observing a value of the sample statistic at least as large as the one observed, assuming the null hypothesis is a true statement. So again, all our calculations are based off of this assumption that the null hypothesis is true. That's going to be this case for all of our different hypothesis tests that we do. So this p-value is a probability. If that probability is small, then that means that our assumption of the null hypothesis is probably false, and so we're going to reject it. And so this argument is generalized here in the form of what we call the one proportion z test. It's called a one proportion z test because it's a claim about a single population proportion, and our test statistic is a z-score. And so the purpose is to test a claim about a single population proportion where the null hypothesis has this generic form, p equals p naught. And so from our data we get x, which is the number of successes in a sample of size n, and then p hat is x divided by n, the sample proportion. Okay. Our test statistic is given by this formula here, which is the same formula that we just derived. And so the critical value is a z-value, p-value is an area under the standard normal density curve. And then this chart here summarizes how to find the critical region and the p-value according to the form of the alternative hypothesis. This chart here is really just a summary of our charts from section 5.1. Okay. Now the requirements for doing this type of test are the following. Number one, the sample is random. That's always a requirement for doing any type of statistical analysis. Number two, the conditions for a binomial distribution must be met, at least approximately. And that's true because this was in our theory, we started with this random variable x, which was the number of successes in the sample, and that needed to have a binomial distribution. And so we need those conditions to be met. So those conditions here specifically are that we have a bunch of trials. In this case, we ask a whole bunch of people the same question. We need each trial to be either a success or a failure, and that's the case here, that each person is either from in-state or out of state. We need them to be independent, and we need the probability of a success to not change from one trial to another. All those requirements, all those conditions seem reasonable. And then the third is that the conditions n p naught greater than 5 and n times 1 minus p naught greater than 5 are both met. And we need those to be met so that our sample proportion has an approximately normal distribution. This was one of the requirements from that theorem 4.1. So to illustrate an application of the one proportion z test, let's look at this simple example. A student claims that less than 25% of plain M&M candies are red. A random sample of 195 candies contains 37 red candies. Use this data to test the claim at the 0.05 significance level. So what we have here is one population. That's all plain M&M candies. And we're interested in the proportion of those that are red. And so the one proportion z test is appropriate. The first step in any hypothesis test is to define the parameter about which the claim is made. In this case, we're making a claim about the proportion of all M&M candies that are red. And we stress the word all here because it's a claim about the large population of all M&M candies, not just the 185 in our sample. So the next step is to set up our hypotheses. So the claim in a mathematical notation is that p is less than 0.25, And so that gives us the null hypothesis p equals 0.25, and the alternative is that p is less than 0.25. Third step is to calculate our test statistic. And so our sample proportion is the number of successes, which in this case the number of red candies, divided by the sample size, and so we get 0.190. And so in our sample we got 19% red candies. Next we calculate our test statistic. Here's the formula. We plug things in and we get our test statistic a negative 1.93. Next we find either our critical value or our p-value. This is a left-tailed test because our alternative hypothesis has a less than sign, and so our critical value is negative z sub 0.05, which from our critical z-value table we get that to be negative 1.645. P-value is the area underneath the standard normal bell curve to the left of the test statistic, negative 1.93. From our z-score table, we find that area to be about 0.02. Okay. Next, we come to our technical conclusion. Our critical region is this interval here, and we see that our test statistic z equals negative 1.93 lies in that region. Also, the p-value is less than 0.05, and so by either criteria, we come to the technical conclusion of that we reject the null hypothesis. And then the last step is to come to our final conclusion. Because the original claim did not contain equality, the final conclusion is that the data support the claim.